Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 6 problem of this month on LeetCode. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with today's problem. Problem number 3479, fruits into baskets 3. Okay, so we have already solved the part 2 of this problem and this is part 3. Okay, so let's see the difference. All right, so first let's read the problem statement. You are given two arrays of integers, fruits and baskets, each of length n, where fruits of I represents the quantity of the ith type of fruit and baskets of j represents the capacity of the jth basket. From left to right, we have to place the fruits according to these rules. Each fruit type must be placed in the leftmost available basket with the capacity greater than or equal to the quantity of that fruit type. Each basket can hold only one type of fruit, and if a fruit type cannot be placed in any basket, then it is going to remain unplaced. Okay, and if it is unplaced, we have to count that. Okay, so we have to return the number of fruit types that remain unplaced after all possible allocations are made. Okay, so if you see this example number 1, these are the fruits, right? So 4, 2 and 5, and these are the baskets. Okay, so first pick this fruit 4. So you have to place this fruit, okay, 4, right, in this basket. Okay, the capacity is 3 only, right? And here value is 4. Okay, so where fruits of I represent the quantity of the ith type of fruit. Okay, so quantity is 4, but basket capacity is just a 3. Okay, so we can't place this, right? But we can place this 4 here. Okay, leftmost, and it is empty also, right? So here I'm placing it here. Okay, done. Right, now for 2, okay, you are again going to search from left to right. Okay, and you are able to place it here. Done. All right, now for 5, again you are searching from left to right, but you will not find any basket where this quantity we can fit, right? So this remains unplaced, right? So we have to return output as 1. Okay, so fruits of 0 is equal to 4 is placed in basket 1 5, fruits 1 is equal to 2 is placed in basket 0 is equal to 3, and fruits 2 is equal to 5 cannot be placed in basket 2 or 4. Okay, since one fruit type remains unplaced, we return 1. Okay, so it is very easy. Just pick one fruit, search from left to right, pick next fruit, search from left to right, pick next fruit, search from left to right. Okay, here we are iterating over n fruits, let's say, and here also we are iterating over n baskets, let's say. Size is going to be n into n. Okay, the time complexity is going to be n into n, that is nothing but O of n square, right? So yesterday, here in this fruits into baskets 2 problem, okay, same example. Okay, so here what I was doing, I was creating this boolean array, and here I'm running one loop, okay, from in the fruits, and then I'm running one loop here in the baskets, right, left to right. Okay, so this is going to take O of n square as time complexity, right? So if I just submit it, I was able to submit this 3477. All right, same problem. If you see the problem statement, same, everything is same. Okay, example is also same, right? Now if I just copy this code here in fruits and two baskets 3, okay, same code, copy here, and if I submit it, then you will find few test cases which got failed. Okay, and the error is going to be time limit exceed. All right, so let's see. Okay, so see here, 737 example test cases are passed, 3 are not passed, right? So we are getting what? We are getting time limit exceeded error. Okay, so what is the difference between part 1, part 2 and part 3? So difference is nothing but constraint size. Okay, so here in part 2, n is just 1 to 100. Okay, so we are able to submit our solution with O of n square. Okay, so we were happy, right? But today when we are trying to submit the same code for part 2, but because of this constraint we are not able to pass, right, all the test cases, so we are sad. Okay, so now what we need to do? Okay, so if you need to know the solution of this part 2, okay, so you can check this video, only 7 minutes, right? Now let's see the optimal solution for this. Okay, part 3 with this constraint. Okay, so this is the only difference. So in this is nothing but your part 3, right? So in part 3, size is 10 to 5. Okay, 10 to 5 into 10 to 5 n square, oh, very big size, right? So now let's see the optimal solution. Okay, so what is the problem requirement? So we need to place the fruits in baskets, right? And each basket has a capacity, right? For each fruit we must find the leftmost basket with a capacity greater than equal to fruit size, and once used that basket becomes unavailable. Okay, so this is the requirement. So here what is the key challenge? Efficiently find and update the leftmost available basket multiple times, right? We are doing the same thing, but we are doing it multiple times, right? Okay, so this approach, a simple approach, is for each fruit, scan the basket from left to right, place it in the first suitable basket, mark as used. Then you are going to get the time complexity of n square in worst case, right? Fruit count into basket count. So it is very slow, right? When n is large. So now what is the optimal solution for this one? Okay, so what we need a data structure. Okay, we need a data structure which helps us quickly find, is there any basket with capacity greater than equal to fruit? Okay, we need to have some data structure. Okay, and which helps them quickly locate the leftmost such basket, quickly update. Okay, mark basket as used. Okay, so this hints at a range query plus update type data structure. Okay, so let me show you here. So if you see, let's take this example only. Fruits is equal to 4 to 5. Okay, fruits is equal to 4, and here 2, and here 5. All right. Okay, and here we have baskets as 3 5 4, baskets as 3 and 5 and 4. All right. Okay, so here this is, let's say this is one half. Okay, and let's say this is one half. Okay, so I need to place this fruit. I need to place this fruit, right? In this first half. Okay, let's say this is my left half, this is my right half. In the left half, okay, in this range 0 to 1, okay, if I just give the indexing, max is 5, max is 5. All right, and in this right, max is 4. Okay, max is 4, right? Okay, we need to place the fruits in the basket from left to right. Okay, this is given in the statement. Okay, left to right. So in the left, if you see, we have some basket available which is having greater size than this 4. Okay, so we have some basket. Okay, so we don't need to check this, then we don't need to check this, right? Then we don't need to check this basket. Okay, we only need to check in this range. Okay, so now if you check, see this range only, this range itself, 3 and 5. Okay, so if I just split it again, this is my left and this is right. Okay, so now what I'm searching for this 4. Okay, so this is nothing but a range 0 to 0, I can say, right? And this is the range from 1 to 1. All right, what I'm searching for capacity equal to 4 or greater than 4, right? In the left, capacity is 3, which is smaller than 4, so in the left my answer is not there. But in the this right side, if I search, answer is there. Okay, in 1 to 1, right? 1 to 1 simply means leaf only, right? This is nothing but 0 1 2 index. Okay, here I'm saying 1 to 1. Okay, only one node. Okay, only one node. After there is nothing, only one node. After that, there is nothing, so I can say this is leaf node. Okay, 1 to 1. My for this one, starting point and ending point is same, right? So here in this 5 is there, right? So that simply means that this basket, this fruit, okay, this quantity, fruit type quantity, can be easily placed in this. Okay, so I'm going to mark it as used. Okay, so let's say I mark it used. All right, so this is why what comes to my mind, that nothing but segment tree. Okay, so because of this range query and update type data structure. Okay, so actually this topic itself, a segment tree, needs a separate video. Okay, there are so many things in this. Okay, so here I'm just going to give the quick recap. Okay, otherwise this video is going to become very lengthy, right? So let's understand quick recap only. I will not take more than 10 minutes or 5 minutes, I think. Okay, so what is segment tree? Segment tree is a binary tree used for efficient range queries and updates on an array. It breaks the array into segments and stores information like sum, minimum, max for each segment, right? So here each node represents a segment L to R of the array. Each node. The root represents the full range 0 to n minus 1. So here for here if you see the baskets, okay, let's say 3 4 5. So here this is nothing but 0 1 2. Okay, so in this range 0 to 2. Okay, so first node, which is going to be root, so it is going to contain, let's say I want to store the max, so in the root node I will have the max from 0 to 2. Okay, then from this I will create one left node, from this I will create one right node. Okay, so this 0 to is nothing but a complete root. Okay, so in this, let's say I'm storing the max, okay, in this root. Now if I go to the left side, so I will have new left. Okay, I want to calculate the mid also. Okay, and that mid, okay, here for this range, my L is this, my R is this. Okay, if I want to calculate the mid, how you calculate the mid? You calculate the mid like this: 0 plus 2 minus 0 divided by 2 okay, so you will get something around 1, okay, mid 1, okay. So next time your, for this one, your left is going to be 0 and your right is going to be mid, okay. And here in this, your left is going to be mid plus 1, okay, that is number 2, and your right is also going to be 2 only, okay. So here, then here initially you have 0 to range, now you have 0 to 1 range here and 2 to 2 range here. Now again you are going to split this, okay. So again you will get, okay, so I will discuss about this example in some time, but this is how what this is what I'm saying here, right? So the root represents the full range 0 to n minus 1. Then how we split the children split the range, left child from 1 to mid, okay, and here right child is mid plus 1 to r, okay. So that's what I was doing here. Left is 0 to mid, okay, mid, right is, this is nothing but mid, and here left is nothing but mid plus 1, so that is m plus 1 2, okay. And here right, all right, this is done, okay. So for the segment tree storage, typically storage stored in an array of size 4 into n. Now this topic also need some separate video, okay, why 4 into n is coming, okay. But let's see, I will explain, okay, why 4 into n we are writing here for safety, enough to hold all nodes, all right. And for this one, the build time complexity is going to be of n, build tree bottom up by combining children results, and the query time complexity is going to be of log n only, traverses only segments overlapping the query range, and update time complexity is also going to be of log n, right, update the value and propagates changes up, okay. So here why 4 into n, why allocate 4 into n for segment tree, all right. So first, segment tree basics, okay. A segment tree is a binary tree, you already know now, right? Each leaf node represents a single element of the array. So here I have explained here, right? Okay, here, so each leaf node, okay, so here 3 4 5, okay, this is the range, then 0 to 1, this is the range, here 2 to 2, 2 to 2 means L and R both same, so here I can write 5, okay. Here L is equal to 0, R is 1, so mid is also going to come as 0 only, okay. So L is 0, R is 0 here, and here L is going to be mid plus 1 1, and R is going to 1, okay. So here 0 0, so here I can say 3, here see 4, okay. So here see all the leaf nodes, in all the leaf nodes I'm writing the this array values only 3 4 5, right, in the end. So 3 and 4, among 3 and 4 what is max, 4 is max, okay, 4 goes here, 4 and 5 what is max, 5. So here in this L to R you are writing 5 as max, okay. So I will discuss this later, okay, but here you are clear with this, right? Then in the leaf nodes I have all the values of this array, all right. Where we are, okay. Each leaf node represents a single element, each leaf node represents a single element of the array, single element of the array, right? Each internal node represents a segment range that is the union of its children segments, okay. Union of children segments, union of children segments, internal, okay. This is the meaning of this line. Each internal node represents a segment range that is the union of its children segments. It is typically stored in a flat array like a heap to avoid pointer based trees, right? So root at index 0 and left child at 2 into I plus 1 and right child is at 2 into I plus 2, okay. Now what is this? This also need one separate video, okay. So here how you are going to write, all right. So here I will try to explain with the example. Let's see this example only then, okay. So here 3 4 5, okay. So here we need 4 into n, okay, 4 into n. So n is nothing but 3 here. So if you create this n is nothing but 3 size, okay. So for safety purpose what we need this 4 into n, okay. Why we need 4 into n I will discuss later on, but here let's understand. If we need 4 into n, so n is 3, so 4 into 3 is 12, okay. So I need 12 here. So here's 0 1 2 3 4 5 6 7 8 9 10, and here let's say this is 11, okay. So here binary, right? So here this is nothing but I will say that this is the value at index 0, okay. I is equal to 0, and I will say that this is nothing but the value at I index is equal to 1. This is nothing but the value at I index is equal to 2. This is the value is nothing but at I index is equal to 3, and this is the value is nothing but at index number 4, okay. So here just add this. So here at 0 you are writing 5, at 1 4, and here 5, here 3, and here 4. These are the dummy or left out, okay. Let's say left out, all right. So here if you see, this is my root, okay. In this root what is the value I'm getting, 5, okay. And this 5 is coming from this I is equal to 1 and I is equal to 2. Okay, so this 5 is coming from 1 and this 2. Okay, clear? Okay, don't worry why I'm writing 5 4. Okay, so just understand why I'm writing, just understand that if I write it like this. Okay, so now this 5 is coming from this 1 and 2. Okay, 4 and 5. Okay, so here I am at 0. Okay, so if I do like this, 2 into I plus 1. Okay, so what I'm going to get, I is 0. 2 into 0 0 plus 1, I will get 1. Okay, so here from 1. Okay, so this is nothing but for my left. Okay, and for my right, 2 into I plus 2 I need to do here. Okay, so if I apply this, I is 0, so 2 into 0 plus 2, I will get a 2. Okay, so from 2. All right. Okay, now what about this 4? So 4 4. Okay, now this 4 is coming from this 3 and 4. Okay, so this is nothing but your 3 and this is nothing but your 4. Okay, so here apply the formula na. This is your 1. Okay, so 2 into I plus 1, 3, and 2 into I plus 2, that is nothing but 4. Okay, so it's right now. This 4 is coming from, if you see, 3 and this 4, right? So this is a formula how we represent left and right. Okay, so 2 into I plus 1. Okay, so now I will explain why we are writing like this, but this is just for this line. Okay, this line. Okay, left child is at 2 into I plus 1 and right child is at 2 into I plus 2. Okay, so segment tree storage basics, root at index 0. Okay, so this formula you already know. Okay, left child is going to be at this particular value. Okay, and right child is going to be at this particular value, and we must ensure enough space to store all nodes. Okay, and here I'm talking after 0 0 is coming from 1 and 2. Okay, 1 is coming from, I'm talking about indexes only. 1 is coming from 3 and 4. Okay, here, right? Now if you see this 5, so now this 5 is coming from, so apply the formula. 5 index is 2. Okay, so 2 into 2 plus 1 is nothing but 5. Okay, and 2 into 2 plus 2 is 6. Okay, 5 and 6, so 5 and 6, there are no such index. Okay, so that's why. So there the max is only 5 itself. Okay, because there is actually these are dummy nodes. Okay, now this is also one question why we are taking this dummy nodes, because of this 4 into n. If this much is enough, that is also one more question, right? Okay, so here first let's see, we must ensure enough space to store all nodes. Okay, so that's what we are discussing here, 4 into n. All right, so leaf nodes, number of elements, you already know that in the leaf nodes we have all the nodes. Okay, all the array elements, right? And the internal nodes about n minus 1 for the balanced tree. What is balanced tree? Okay, so let's say this is one node. Okay, and this has both left and child, left and right. Okay, and then this node also has left and right. Okay, left and right. All right, so let's say your n is 4. All right, n is equal to 4, right? N is equal to 4, so this is nothing but two values here. Okay, a b c d. Okay, and now if you see at this level we have n by 2 values. Okay, here 4 and here just 2, and here we have just 1. Okay, here we have just 1, right? So now here if you see, uh here we have 4. Okay, 4 leaf nodes is equal to number of elements n, and internal nodes. Okay, these are leaf internal nodes are nothing but, if you do this n minus 1, what is the value you are going to get? 4 minus 1 3. Yeah, 3 are there, 1 2 3. Okay, so for balance 3, internal nodes is equal to n minus 1. Okay, so n minus 1, these many nodes, these nodes, and these are the n nodes. Okay, so in total how many nodes are there? N, which are leaf nodes. In this I'm going to add the leaf node, these internal nodes are n minus 1. Okay, so what is the value that I'm going to get? I will get 2n minus 1, right? So total is equal to 2n minus 1 nodes for the perfect power of 2 arrays. All right. But when n is not a power of 2, we add up to the next power of 2, which increases the nodes. Now let's understand this line. Okay, so this case one you already clear, right? So here in the array you have 4. Okay, so you have n value as 4. All right, n value as 4. Okay, so here this 4 is the perfect multiple of 2. Okay, so 2 power 2 if you do is nothing but 4. Okay, so clear. So now here in this, how many total nodes will be there? Total, if you see, for 4, 1 2 3 4, we have 5 6 7. Okay, 7. So how you're going to get 7? So that is very easy. Okay, 4, what is the next power of 2? Okay, next power of 2, which is greater than this 4. Okay, so 2's power are 1 okay, then 2, okay, then 4, then 8. Okay, so this is what's coming, right? 8 after this, right? So 8 minus 1 I can do, if I do 8 minus 1 I will get 7 only, right? Here I proved not that 7 are there. Okay, so here what is the next power of 2? Next power of 2 is nothing but 8, right? So here in this 8 if I subtract 1 I will get 7. Okay, same way take any other multiple of 2. Okay, so we have 8 is nothing but 2 power 3. Okay, and here after 8 what after 8 16 will come now, right? Here I'm just writing the powers of 2, right? Okay, so here here how many nodes will be there? Okay, this is nothing but 2 power 3, but how many nodes will be there? So number of nodes will be next power of 2. If I do after this 8, after this 8 we have 9. 9 is power 2, no. 10 is power 2, no. 11 is power of 2, no. 12, can we form 12? No. Can we 12? 13, 14, 15, yeah, 16, right? 16. Okay, 2 power 4 if I do I will get 16. Okay, so here I write 16. 16 minus 1, that is nothing but 15. Okay, so that is nothing but number of nodes I'm going to get. Okay, so here same way if you do 16, 16 is nothing but 2 power 4. Okay, perfect. This is a power of 2. Okay, 16, right? Okay, n is equal to 4, this is power 2. N is equal to 16, this is also power of 2. Okay, if I do 2 power 4. Okay, so after 16, 17, 18, 19, 32. Okay, 32 minus 1, so I will get 31. Okay, 31 number of the nodes. These are the nodes that I'm getting here. Okay, so these are the nothing but nodes required. Nodes required, nodes required. I can also write this 7 like this now. This 8 as 2 power 3. Okay, this 16 as 2 power 4 minus 1. This 32 as nothing but 2 power 5 minus 1. Okay, so here you should see 2 power 4 minus 1. Okay, this is nothing but n value, right? And here 2 power 4 here in this case. Okay, when your n is 8, so here what you are writing 2 power 4. Okay, 2 power 4, right? Okay, and here what you are writing in this case 2 power 5. Okay, so this 2 power 8 nodes required 2 into 2. Okay, but we can write it 2 power 3. Okay, 2 power 3 minus 1, right? And here 2 power 4 minus 1. All right, so here it is writing like this: 2 into 4 minus 1. Okay, 2 into 8. Okay, so okay, yeah, this is also correct now. Here here it's like this now. 2, next here this is nothing but 2 power 2. Okay, so here this is nothing but 2 power 3. Yeah, okay, so here 2 power 3 into 2 is nothing but 2 power 4. That's what I'm writing here. Okay, don't get confused. 2 into 4 is nothing but 2 into 2 power 2. That is nothing but 2 power 3. Okay, that is what I'm writing. Okay, so 8 minus 1. Okay, so it is a writing extra here, but don't worry. Okay, next power of 2 now. Next power of 2. So what you are doing, 2 into 8. Okay, next power of 2. So here if you, this is the example. Okay, I prove it now. Let me prove. 4 4 7 you already know here. Okay, 4 16 also. 4 16 also. If you 4 16 4 8. Okay, 16 is very, very big. Okay, for 8 leaf nodes. Okay, 1 2 3 4 5 6 7 8. Okay, we are still actually going over the basics only of segment tree. So here if you see 16, okay, they will have one here. Okay, then they combine will have one here. Okay, they combine will have one here. Now they combine will have one here. Okay, so here 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, see, we are getting 15 only. Clear? Okay, 15 nodes only for n is equal to 8 leaf nodes. For 8 leaf nodes we are getting total number of nodes as 15. Okay, right? Clear? And this 8, how we are going to write this? 2 into next power of 2. Okay, so 2 into this 2 into 3. If you do 2 into 2 into 3, okay, you can say, here I'm writing 2 4 na, 2 power 4, so you can say 2 into 2 into 3. Here I'm writing 2 into 3, so you can say 2 into 2 into 2. Okay, so whatever value you are going to get, just subtract 1 from it. Okay, you will get the number of nodes. All right, okay, clear? Okay, these are number of nodes required. But what is the case when my n is equal to 5, which is the known power of 2? Known power of 2, right? N is equal to 5. 5 leaf nodes. Now there is some issue. Okay, this is good. Okay, this is good. Now what? Now how I'm going to divide it in half here? Okay, it's not possible. So now for n is equal to 5, n is equal to 5, it is not possible further. So now how I'm going to solve it? So here what I'm going to do, I'm going to create one few dummy nodes. Okay, so here let's say I'm going to create this like this here, right? done. Okay, and I have to create a few more now. If I just do this, okay, I will get here. Now again this is issue now, right? So here also I will create two more. Okay, and here these are dummy nodes I'm creating. Okay, and they will also give me one here. Okay, now if you see, now I can easily combine these two. Okay, okay, so now it is possible, right? So how many dummy nodes I'm creating here? Okay, so this is the actual node, actual node, actual node, actual node. But here after this, if you see this, okay, this, okay, these are the dummies that I have created. Okay, these are the dummies that I have created, right? Okay, so now in total how many we have now? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. Okay, we have total 15, right? 15. Okay, or I can say 16 minus 1, or 16 minus 1 I can say 2 power 4 minus 1. Okay, and what is this 2 power 4? 2 power 4 I can write it like this: 2 into 2 power 3 minus 1, right? And 2 into 2 power 3 minus 1, if you see, this is what I was writing here. Okay, 2 into 4 minus 1, or you can write 2 into 2 power 3 minus 1. Okay, same thing, right? So this is nothing but for 8. Okay, for 8, but in actual we have n is equal to 5 only, right? So for 8, 15 is good, but for this 5 also, what we are getting? We are getting 15 only. Okay, because of these dummy nodes in total. Okay, total, because we have added some dummy nodes. Okay, so here in case when my n is equal to 5, okay, when it is a non-power, one second, when it is a non-power of 2, okay, so in that case what you need to do, so n is equal to 5, so what is the next power of 2? Next power of 2 is 8. Okay, after 6 7 then 8. Okay, so once you get that, okay, in this also take one more 2. Okay, multiply it with the 2. Okay, so you are getting here 2 power 3 now. So instead of 2 power 3, take as a next power. Okay, number of nodes required as 2 power 4 minus 1. Okay, so that in that way you're going to get 15. Okay, so for n is equal to 10, so n is equal to 10, after that you have 16. Okay, which is which comes in the power of 2, right? So 2 power 4, right? So 16, after 16 we have 32. Okay, so in that 32 we subtract 1. Okay, but if my n is 8, okay, so after 8, what comes after 8? After 8, uh if my n is equal to this, okay, so that is nothing but 2 power 3. Okay, so in that case how many number of nodes required? So after 8 what comes? After 8, 16 comes, right? Okay, after 8 16 comes. So in that case just take that 16 and subtract 1. Okay, not take after 16 after and take 30. Okay, so in that case n is equal to 8, we just need 15 only, right? So here if you see here, right, for 8, okay, and here for this example 8, so only 15 are required, right, nodes, right? But if n is equal to 10, okay, so that simply means until 8, okay, which is a perfect power of 2. Okay, so 15 is fixed. Okay, but if my n is 10, right, then we need further, then we need more. Okay, then we need more, right? Then it is not going to fit here inside this only 15. Okay, then what we need to do, we need to take the next power of 2. Okay, then nodes equals into 2 into this next power of 2. Okay, then minus 1. So this is done. Okay, so now here for n is equal to 5, okay, so we are taking some extras, right? So initially we have, okay, n is equal to 5, and then we are taking some extras. All right, so now I'm going to drive the formula. Okay, so n is equal to 5, okay, and n is equal to 5, then we are taking some extras. So here how many we are taking in the leaf? I can say 2 into 5. Okay, 2 into 5 is 10. Okay, I will say that this is nothing but approximate, this is nothing but approximate value, 2 into n. But how many we are taking? We are taking 8. Okay, very close. 10. Okay, I'm just multiplying it with 2. Okay, so that we can easily split this in the here. Okay, we can easily split here, right? We are splitting in half half now every time. So if I just multiply it with 2, I will get that. Okay, so it is not actually 10, it is just 8 only, but here I'm just writing it 2 into 5. Okay, 2 into 5 is 10. Okay, why I'm taking this? Because 5 is not divisible by 2, right? But if I just do 2 into 5, then I divide it with 2, then it is divisible by 2. Okay, so in every part I'm cutting it in half now. Okay, I'm cutting it in half, I'm cutting it in half, right? 8, then 4, then 2, then 1. Okay, so that is why I'm taking 2 into n. Okay, but in actually it is nothing but it is for 8 only, but it is very close, it is very close. Okay, so same way if you take this n is equal to 10 example now, so here also you will have 16 in total. Okay, if you take, okay, so here n is equal to 10, n is equal to 10 value. Okay, so 10 1 2 3 4 5 6 7 8 9 10. Okay, so here let's say they are making this, okay, this, they are making this, okay, they are making this. So here also you need some dummies. Okay, so how many dummies you need here? 10, next power 10, 2, if I do 16, okay, 16 we get here. Okay, 1 2, okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 I will get. Okay, so now if you do this, now you will be easily, you will be able to split all this in half. Okay, this, so then these two, these two, these two, these two, okay, then these two, then these two, and then these two. Okay, so you're going to get like this. Okay, so here some nodes, okay, some node here, some nodes here, some nodes here. Okay, this is what, right? So for n is equal to 10 also you're getting 16. Okay, but I will just say approximate this as 2 into n. Okay, so that I can easily divide. Okay, I will just say this is nothing but approximate value, approximate value. Okay, so here I'm taking approximate value. Okay, don't get confused that why I'm writing 2 into 10. Okay, this is just approximate. Okay, so here in this level, okay, now see carefully, I'm going to drive that formula. In this level we have 2 into n. So in this level we are going to have some half, let's say n. Okay, then in this half we are going to have some more half, n by 2. Okay, so what is happening? First number is 2 into n. Okay, then after that we have what, we have n, then after that we have n by 2. Okay, then somewhere it ends. Okay, so let's say this is one series. Okay, so here see n, okay, this is multiple of, this is the first number, then it's half, then it's half. Okay, so this is nothing but gp. Okay, if you calculate the sum of this in gp, okay, the total number of nodes, formula is a is equal to 1 minus r, right? So a first number is 2 into n. Okay, and here 1 minus this r is nothing but difference. Okay, so n divided by 2 into n. Okay, so this is how you calculate now, that is nothing but 1 by 2. Okay, so much extra thing we are doing here. Okay, so this is nothing but half. Okay, so 2 minus 1, so 2 into n here, and here what we are going to get, 1 divided by 2. Okay, here n is going to cancel out half. Okay, so this is nothing but 2 is going to go up, 2 into 2n, so that is nothing but 4n, so that is by 4n is coming. Okay, so it's a lot of discussion. All right, so here that's why we are going to allocate this. Okay, so that we stay safe. Okay, we stay safe, right? So that is the reason we are going to take 4 into n always, right? And if you see here, the approximate value whatever I'm taking now here, 2 into n that we are taking, okay, I'm getting 10. Okay, but only 8 are required, so we are good now, we are taking max only. Here see n is to 10, 2 into 10, and I'm going to get 20, but only 16 required, but we are staying safe. Okay, no issue if we are taking one extra space in the segment tree. Okay, so that's the reason. All right, this is done. Okay, so now how we are going to solve this problem? Very easy. Okay, so now here, without wasting any time, let's see. Okay, so here these are the fruits you have, right? 4 2 5, 4 2 and 5. Okay, and here in this baskets, let's just apply the segment tree. Okay, so we have already created this segment tree. Okay, so 0 to 2 range, then 0 to 1, then here 2 to 2, then 0 to 0, 1 to 1. Okay, so now 4 I want to place. Okay, so 4, you come here, you see that this value is 5. Okay, this is the max value in this complete range. That simply means this 5 is bigger than 4. That simply means that I can place this fruit somewhere. Okay, but if this value itself is smaller than this 4, then that means definitely we can't place this fruit. Okay, but right now the topmost value, which is for complete range L to R, okay, 0 to 2, okay, 0 1 2 index. Okay, so that simply we can place. Okay, now in the problem statement it is given that we have to search in the left space only. Okay, so first we go to the left space. Okay, this here, so here but we have 4. Okay, we have nothing but 4. Okay, so here, but we have here what I'm writing, okay, here 5. Okay, okay, so here, yeah, in this space. Okay, so in this range 3 into 5. Okay, 3 into 5, this is the range now I'm checking. So in this range, okay, so here why I'm writing here it should 5 now, here this. Okay, let me do one thing, let me write this. Okay, I think here 5, and here 4, and here 0 to 0 na, 0 0 you have 3, and 1 to 1 here you have 5 na, actually, right? And here 3 5 5 max. Okay, and here it is nothing but 4. Okay, so 5 4 5 and 3 and 5. Okay, so this is how your tree actually. Okay, so just we have written 4 here mistakenly, but okay, so no issues. So here this is what you need to do. Okay, so here let me do one thing now, let me draw it again. Fruits is equal to 4 to 5, fruits is equal to 4 to 5, and what is the
value in the segment tree baskets. Okay, let's apply the segment tree here. Okay, on baskets 354. All right, in baskets 3 baskets only we have to search now, right? 354 in which we have to place or not. Okay, all that stuff. So here first 0 1 2 complete range. Okay, complete range. Okay, so your left is 0, your right is 1. Okay, and this is nothing but index is 0. Then your mid is going to be right is 2 now, so mid is going to become as 1. Okay, right. Okay, so now here in the left half, okay, in the left half your L is going to be 0. Okay, and the right is going to be until mid, okay, which is 1. And here in this half your left is going to be mid plus 1, that is nothing but 2, and right is also going to be 2 only, right? Okay, so now here if you see both L and R are same. Okay, so 2 into 2, here we have 4, so I'm going to place 4 here. Okay, now in this half again your mid here is going to be uh 0, right? Right, 0 plus 1 divided by 2. Okay, mid 0. Okay, and here this is for index is equal to 2, and this is for index is equal to 3. Okay, so now for index is equal to 4. Okay, here what you are going to get, you are going to get L as 0 and R as 0. Okay, both L and R same, so at 0 we have 3. Okay, and here at index is equal to 5 we have L is equal to 1 and R is equal to 1, so we have 5 here. Okay, so 3 and 5 max is 5, and 5 and 4 max is 5. Okay, so this is your segment tree. Okay, we have created. Now here we want to place this 4. Okay, so for this 4, this 5, okay, 5 is bigger than 4. Okay, so that simply means that we can place this 4 somewhere. Okay, so now I'm going to come here. Okay, so here I will see that I have 5. All right, so okay, so here I come to this left. Okay, in this we have 5. Okay, so that simply means here also let's find out if we can place 4. Okay, somewhere. So in the left side here we have 3 only capacity, right? Basket capacity. Quantity is 4, so we can't place here, right? But we can place here in the right side. Okay, so if we can place here, so what I'm going to do, I'm going to make it as -1. Okay, I'm going to, since I've used it now, since I've used it, I'm going to make it -1. Okay, so mine, if I'm going to do it -1, okay, so I'm going to simply return true from here, that I'm going to place this. Okay, simply return true. Okay, so if this is possible, okay, return true here, return true, and do one more thing here. 3 minus 1, what is the maximum of them now? 3. Okay, so just update it to 3. Okay, this is done. Next time you are, okay, so 4 you have placed it here. Okay, now next time you have 2. Okay, so 2 5 is greater than 2. Okay, come to left. Here 3 is greater than 2. Okay, then come left. So here also we can place this now, so just place it here. Okay, this 2 in this 3, and just update it to -1, and -1, what is the max? -1. Okay, that's it. Okay, so here -1, and you are going to return to that we are able to place. Okay, the next time you are going to search this 5. Okay, so 5 here in the left we have -1. Okay, no need to search further. Okay, so see, there is no need to for further search. Okay, here we have already used. Okay, so we are just simply going to skip here. Now we are directly coming here. Okay, that is the benefit of this. All right, so here we have 4. 4 is also greater than, 4 is also smaller than 5. Okay, so that means we have to return false from here. That simply means that it remains unplaced. Okay, if it remains unplaced, simply count it. Okay, so only one fruit remain unplaced, so our output is 1. All right, so let's write the code, and with code you guys will get better understanding. Okay, so these are some basics of segment tree. Okay, and if you need detailed video on this symmetry, then just write the comment. Okay, whenever I get a chance I will try to make the tutorial of this symmetries. Okay, all right, so now let's write the code for this. So this is the code for fruit into baskets part 2. Let me reset. Okay, now here let's write the code. All right, int n is equal to fruits dot length. Okay, and here we are just going to create the segment trees to store the maximum basket capacity in a range. Okay, so for that, int, and here you have to write 3 is equal to new int 4 into n. Okay, 4 into n. All right, and now we have to build the tree initially. Okay, so here I'm just going to call the method build tree. Okay, so in the build tree, what I'm going to pass, I'm going to pass 0 0, and here I'm going to pass n-1, and here I'm going to pass baskets array n-1, and here I'm going to pass the baskets array, and here I'm going to pass the tree. All right, so what I'm passing here, okay, in this build tree I'm passing the node. All right, and then I'm passing the left, I'm passing the right, and then I'm passing the baskets, and I'm passing the tree. Okay, the tree that I'm going to create. Okay, the build tree, right? So here let's say I build the tree here. Okay, so now I have to count the unplaced ones, right? Unplaced fruit. So here I'm just going to create one variable for that, unplaced count. Okay, and set to 0. Now we have to try to place each fruit. Okay, so let's say here I build the tree, and here I'm just going to count the unplaced count. So here I have to iterate over the fruits, right, one by one. So here int, and let's say fruit quantity is given, right? Fruit quantity. Okay, and here in my fruits I am to iterate. All right, and here boolean is placed. Okay, so here I'm going to check the value of this is placed. Okay, so here also again I'm going to call the one method place fruit. Okay, so it is going to check if we are able to place the fruit or not. Okay, so here also what I'm going to do, I'm going to pass 0 0, and then I'm going to pass n minus 1, then I'm going to pass the tree, and then I'm going to pass the fruit quantity. Okay, so now what we are exactly passing here, 0 0 0. Okay, okay, so here, but this is nothing but my place fruit, right? So in place fruit we are again passing the node. Okay, we are going to pass the left, we are going to pass the right. Okay, we are going to pass the tree. Okay, this tree, one second, this tree, and we are going to pass the, after that we are going to pass the fruit quantity. Okay, the fruit quantity that I'm passing. Okay, so I'm going to check this. All right, so here now, here if we are not able to place this. Okay, if is placed value comes out as false. Okay, let's say is placed value is going to give me true or false. Okay, it is going to check if we are able to place or not. Okay, if we are not able to place, then we have to just increment the value of this unplaced count. Okay, unplaced count plus plus, let's say. Okay, done. And in the end we have to just simply return unplaced count. Unplaced count, that's it. Okay, so now here let's write the method. Okay, this is the main thing, build tree, and you are going to use this same code, okay, many times in many other problems also. All right, so here we have to build a segment tree storing the new capacities. Okay, so here what you need to do, private void, and here build tree. Okay, this is what you are passing, and here what you are passing, int node, int left you are passing, int right you are passing, and here you are passing the baskets. Okay, baskets, and you have to create the tree. Okay, so int tree array you are passing. Okay, the array that you have created here, this of size 4 into n. Okay, so now let's write the code. It's very simple. Okay, so here when you are going to get the leaf, where is the tree, where is the tree, where is the tree, when your L and R both are same. Okay, so here base condition, if left is equal to right. Okay, so this is important. Okay, so here listen carefully, if this is the case, then tree of node value, okay, tree of node value, right, in this case just update it as baskets of left. Okay, baskets of left. All right, and here simply return from here. All right, so if left is equal to right, okay, if left, okay, if your left becomes equal to right, then in that case the tree of node value, okay, whatever the node value you are going to pass, just you are going to update that baskets of left with the baskets of left value. Okay, and then simply going to return. Okay, so how we are going to get that? Okay, so first here let's see, first we have to calculate the mid. Okay, so mid you have to write simple left plus right minus left divided by 2, or you can simply write left plus right. Okay, and here right like this, left plus right divided by 2. Okay, that's it. Now here you have to form the build tree. Okay, left part and the right part. So here if I can do one thing, I can copy this. Okay, and okay, so we have to form the left and right part now. So here what I'm going to do in that case, here just paste it here one time, place it here one more time. Okay, and here now here what we are passing, we are passing a node now. So next time my left node, okay, I have to form the left part and right part. Okay, so I can say it, I can write it like this. Okay, for left, for right I can write it like this, 2 into node plus 2, right? Okay, and here what we are passing, we are passing left. Okay, and here we are passing next time my right is mid. Okay, for the left, and for the right my left is going to be mid plus 1, and my right is going to be here right only. Okay, right only. All right, okay, so here you can say right. right. Okay, this is done. So this is done, and here you have to update the tree node. Okay, tree node here, like this. Tree node is equal to, so how we are updating the tree node, it is coming out as the max of 2. Okay, so left and right, whatever the max value. All right, so here I'm just going to write math.max, and here I'm going to write tree. Okay, and here I'm just going to pass 2 into node plus 1. Okay, and here I'm just going to pass 3 2 into node plus 2. Okay, and this is done. All right. Okay, so this is how you're going to write. All right. Okay. Okay, so now once this is done, then we have to find the leftmost basket with the capacity greater than equal to fruit quantity, and then we have to mark it used. All right, so for that, what you need to do here, just write one more method, private boolean, and here place fruit, and here also again you have to pass the same thing na? Int node, one second, here int node left right baskets. Okay, no, not basket, you need tree only. Okay, so here let me just paste it, and here you need tree. Okay, tree, and you need what, the quantity. Okay, fruit quantity. So fruit quantity. So here what we are doing, let me add the comment also. Okay, so find leftmost basket with capacity greater than equal to fruit quantity, and we have to mark it used. Okay, this is also going to be very simple code. Okay, this part also, right? Okay, so here if no basket in this segment, then we can hold the fruit, right? So if tree node itself, okay, tree node, if tree node is less than fruit quantity, okay, in that case simply return false. Okay, if it is false, then we are just going to update this unplaced count. All right, this is done. And here if a leaf node, then we have to use this basket. Okay, so when it is leaf node, when my left is equal to right, then it is leaf node. So in that case, tree node, okay, is equal to -1, make it as used, and then simply return true. Okay, done. Then here also how we are going to calculate the mid. Okay, which side we need to proceed. Okay, mid is nothing but left plus right, and here divided by 2, and here create one boolean placed, and here we have to prioritize the left child to ensure leftmost basket. Okay, so here what we need to do, we have to just check first left side only. Okay, so if we have to prioritize the left side. Okay, if tree node into 2 plus 1, okay, if this value is greater than equal to the fruit quantity that you have. Okay, so in that case, placed, okay, the placed value. Okay, so in this I'm just going to call this place fruit again. So this place fruit, this one. Okay, so now this time if in the left side it is possible now, proceed to the left side. Okay, so place fruit. So here also you have to write 2 into n plus 1. Okay, and here left side proceeding now, so you have to write left here, and here this side you have to write mid. Okay, and here you have to pass tree and fruit quantity, right? This is done. And in the else part, copy this. Okay, paste it here. Now for the right side, so here 2 into n plus 2 you have to write, and here in the left you have to pass mid plus 1, and here in the right you have to just pass simple right. Okay, done, right? So we have to prioritize the left child to ensure leftmost basket. Okay, so once this is done, okay, once this is done, so we have to update the current node after placement. Okay, so current node, so we are checking the left and right side now. So current node is going to be tree node. Okay, so in this we have to just update the max. Okay, so if any becomes -1 na, so 3 -1 I shown you now here, somewhere here, yeah, here -1, then -1, so then we have to update -1. Okay, so from 5 it becomes 3, then -1. Okay, this step. So here I'm just going to write math.max. Okay, and here tree node into 2 plus 1 for the left side, and here copy this. I think this will work. Paste it. 1 second. Copy this complete. Paste it here. 3 into node into 2 plus 2, right, for the right side. This is done, and here you have to just simply return the placed value, whatever the placed value you have. Okay, this is done. So this is your code. Now let's run the code and see if there are code issues. So yes, there are some issues, so let's fix that. It is node, node n, just make it node. Okay, and node e. Now let's run it again and see. So see, all the test cases has been accepted, right? Now let's submit it. So see, our solution is accepted now, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you in the next video. Thank you. Bye bye.